Okay, guess it's about time to resume. Thank you for your endurance, sticking it out for 2 extra sessions. So let me just remind you of where we were. We're in the process, we've reduced matters to proving this localized estimate for the local half-order time derivative, okay? And remember, F was the projection of F star, and F star was the subset of the big surface cube on the boundary where the caloric and adjoint caloric measures had averages that were roughly like 1, okay? Again, QR is QR of some fixed center x tilde t tilde in Rn, okay? And so now I'm going to define a subdomain of the half space so this will be actually in I, let's say 50R of 0 x tilde t tilde, right, the same center, such that R is bigger than h of ys. So it's the domain above the graph of h of ys, and remember that h of ys is comparable to the distance of ys to the set F, but this one is regularized. So it's a regular Lipschitz function. That was one of our lemmas, lemma 4 maybe. It said we could do that, okay? So now I'm going to set A star. I'm going to define a new function A star. It's going to be our original function A, which is the function that defines the graph of sigma, or the graph of A defines sigma, that's what I should say, plus C1 times H, where C1 is a small constant, small but uniform, small enough, I should say. And in fact, we can be explicit. C1 is going to be the implicit constant in Lemma 7 it was, such that A of h of ys, comma y, comma s. Remember when we write A with this third vertical parameter, that's the function whose graph defines the level set at this height, okay? So remember, Lemma 7 said that this difference was on the order of h of ys, all right? And so in particular for the lower bound, C1 is going to be the constant for which this holds, all right? So then we're also further going to define a domain omega star, which is going to be the set of y naught, y, and s, such that y naught is bigger than a star of ys. Okay, so notice here that we've lifted up from the original boundary by a little bit, but not very often, because we're only doing this. This is only a lifting when we're away from F, or when the projection is away from F, right? And remember, F is or F star up on sigma is a big portion, a very, very large portion of the original surface bulk, okay? So this is sort of a pseudo Sawtooth domain. All right, so we have This is our original sigma. And whenever we're on F star, we've lifted it up just a little bit like this. And this is some more of F star. Maybe we lift up just a little bit. Okay? Sort of a regular way that's kind of like it's like a regularized sawtooth bump. Okay? And then omega star is above this guy, right? Okay. All right. So now I'm going to state some corollaries of Lemma 7. Again, Lemma 7 said that one actually had comparability here. All right. So the first one is that if R, Y, and S is a point at omega 1, then A of R, Y, S, comma, Y, S is an omega star. All right. And so the proof is easy. By vertical monotonicity, if RYS is in sigma, RYS is in omega 1, and remember what that means. That just means R is bigger than H of YS, then A of RYS is bigger than A of H of YS. That's just the monotonicity. But we have an estimate for this guy. It's going to be bigger than or bigger than or equal to A of YS plus. Bigger than or equal to, maybe I want it to be strictly bigger. All right, which we can do. Plus C1H of YS, and that is A star, right? Oh, actually, it could be less than or equal to, because I want the bigger than here. Yep, that's all right. It can be less than or equal. Okay, and this is A star. All right, which is the statement. Okay, so there's basically nothing to it. Okay. All right, and now I'm going to define some slightly tweaked versions of A star. A double star is going to be A plus, let's say, C1 over 2H, A triple star, and at some point I realized this is not the greatest notation in the world, but we're stuck with it now. I'm sorry. A triple star, we have C1 over 4H, and A quadruple star is going to be A plus C1 over 8H. And so then when we define the corresponding domains, omega double star is going to be the set of Y naught YS such that Y naught is bigger than a double star of YS, and so on. Notice that each of these is sort of a successively fattened version of the previous one, right? Because the boundary in each case, we're lifting it up a little less off the original boundary, okay? All right. So then we have the following corollary. The numerology here is maybe a bit deceptive. This isn't really a corollary of Lemma 7. It's really a corollary of Lemma 6. Okay, Lemma 6 was the one about averages of the caloric and adjoint caloric measure. I'll remind you in a second. Okay. So let's let y be a point in even the largest of these subdomains, omega quadruple star. Then we have the following, that the green function at y divided by the distance to the boundary is like 1. And that's also like, well, remember, this was a normalized green function. Also like the normalized adjoint green function. Okay, where g tilde of y is, again, with the same normalization, multiply times the sigma measure of delta star. Then we have g of y with pole at the time backward corkscrew point relative to delta star. Okay? All right, so remember, this guy is actually an adjoint solution, and this guy is a solution. It's a solution of the equation, okay, in this variable. All right. All right, and so the proof is, again, easy. Remember, the distance of y to the boundary is comparable to the vertical distance. And this is going to be bigger than C1 over 8 h of ys by definition of omega quadruple star. All right. So now we apply Lemma 6, or to be more precise, estimate star in the proof of Lemma 7, right? Which discussed the case where the distance to the boundary is, or where if we look at it with a value rho equal to delta of y star, or y, bigger than or equal to h of ys. And we get that the average over this on the surface cube at this scale centered at y of k star is like 1. That's exactly what estimate star says. And this was just a consequence of Lemma 6, really. Okay? And we didn't state it, but also the same thing holds for the adjoint caloric measure, the normalized adjoint caloric measure as well, because again, it only utilized Lemma 6, which applies to both of them. Okay? All right, and now we just use CFMS. Okay, with this scale. Okay? And then we get the estimates for the green function. Okay? So the green function is comparable to distance to the boundary here. All right. One more corollary. Is that for R, Y, and S, in omega 1, we have R is actually comparable to the distance to the boundary of A of RYS YS, which is comparable to, of course, once again, the distance for a Lipschitz graph domain is comparable to the vertical distance. So this is comparable to A of RYS minus A of YS. Okay? And the proof is the following by Corollary 7a that we just proved. A of RYS is in omega star, right? If RYS is in omega 1. Okay? So then by Corollary 7b, since omega star is contained in omega quadruple star, we're going to apply it with y equal to this point. We get that we obtain that 1 is comparable to g of y over delta of y. But this y is this point on the level set, right? This y is this point. This is a point on the level set, so g at that point is by definition r. Okay? So that tells us, that gives us this. All right. Okay. Next lemma. RXT being omega 1. Then we have the following. First, if we differentiate A of RXT with respect to T, it's going to be less than or equal to the absolute value of dt of g evaluated at psi of RXT. Remember, psi of RXT, this was shorthand notation for A of RXT, comma x, comma t. Okay? Point on the generic point on the level set. All right? Second, if we take a spatial gradient either in the r or x variables of A, it'll be at most some uniform constant. 3, if we take two spatial gradients, that's going to be controlled by two gradients of g. I guess, just to be clear what I'm saying here, this is the t derivative of g evaluated at this point. It's not the t derivative of g of this point, which would entail differentiating t twice. Okay? Same here. Okay, so it's the double spatial gradient of G evaluated at this point. Okay, fourth, if I mix a spatial gradient and a time derivative of A of Rxt, this is going to be less than or equal to spatial gradient with a time derivative applied to G. Again, I won't keep running this, always evaluated here, plus a product of dt of G times grad squared G. All right, and finally, the fifth one, we take R times dt of A plus R times grad squared in the spatial variables of A plus R squared times triple gradient of A plus R squared times one spatial gradient and one time derivative. All of that's going to be bounded by uniform constants. Okay? All right. So let me just give you a sketch of the proof because all of these estimates are proven in more or less the same fashion. So I'll just do one to give you the idea. Okay. So this is just an exercise in implicit differentiation using these Alt-Caffarelli lemmas that tell us that we have strict positivity for the vertical derivative of the green function. Okay. All right. Okay, to be a little more precise, here's what we do. All right, by definition, G evaluated at psi of Rxt. This is a point on the level set, so this is R. Okay, so if we differentiate with respect to T, that's just going to be 0. But now carry out this differentiation, all right? Remember, psi of Rxt is A of Rxt, comma x, comma t. All right? So this equals dt of A of Rxt times dx naught of G evaluated on the level set, plus dt of G, again, evaluated there. Okay? Now I'm sure you already see how this is going to go. Oh, okay, sure. Is that good? Okay. So of course, what does that say? That says that if we look at the absolute value of dt of G, it's going to be dx naught of g times absolute value of dt of a. And of course, we know that this one is like 1. All right, because, all right, so this is, in other words, this is just like this. Because by lemma 3, dx naught of g at a of r xt, xt is like g of a of r xt, xt divided by delta of a of r xt, xt, and this is r over delta, again, of the same thing. And we just saw in Corollary 7c that this ratio is like 1. Okay? All right? And the other ones are proved in the same fashion. It's just implicit differentiation plus using this fact over and over and over again. Okay? When you pick up the vertical derivative of g, it's going to be like 1. All right? Okay. Next lemma. Maybe I'll give this a name. This is a local square function estimate, or Carlson measure type estimate on omega 1 for derivatives of A. Okay? With some uniform implicit constants. Remember, R is always the ambient scale on which we're working. Okay? Capital R. All right? Okay. All right, so let's prove this. All right, so let me begin with a claim. Is that the left-hand side of star, this guy, the thing we're trying to bound, is itself bounded by, let's call it double star, the integral over the domain omega double star, this slightly fattened version of the sawtooth, the regularized sawtooth, of delta, distance to sigma, times dt of g squared, plus delta spatial gradient of g squared, plus distance squared times grad dtg squared times 1 over distance to the boundary dx naught dx dt. Okay. So let me give you a sketch of the proof of the claim. Maybe just pick out one particular term. All right. This is going to be a consequence of lemma 8. Okay. For example, by lemma 8, we have that r times dt, and also corollary 7c. We have that r times dt of a, that rxt, is less than or equal to, okay, corollary 7c says that r is comparable to delta on the level set. So we get to put here delta in place of r, delta of a of rxt, comma x, comma t. And then lemma 8 said that the time derivative of a is controlled by the time derivative of the green function. Again, evaluated here. Okay. All right. Which in turn, if we use local boundedness estimates, Moser type local boundedness, although for the constant coefficient heat equation or adjoint heat equation, this is more classical and elementary. All right. But what it says is that you have a solution. This point the bound at any point is controlled by an average over a box or parabolic box or parabolic ball centered at this point, whose scale is like the distance to the boundary. Okay? So this is going to be less than or equal to delta, once again, of a of r xt times an average over a ball, let me say it's of radius, let's say delta 1. I'll tell you what delta 1 is in a second. Okay, so we'll have an L2 average. Okay, where delta 1 is going to be delta of, it's going to be this delta. This is the scale we're working at, which of course we know is on the order of r, divided by some sufficiently large constant n, where n is chosen large enough that if a point x is in omega star, which this point is, remember, then the parabolic ball of radius delta 1, centered at that point, will be contained in the slightly fatter omega double star. Okay? All right, and now you use Fubini's theorem to see that this guy is controlled by this guy. You dominate that term by this, use Fubini's theorem, okay, and then you get that. And the other terms with different derivatives work the same way. Okay? So this proves that, well, It proves the claim at least for the one term, and then the other terms work the same way. So it's enough to prove that double star, in turn, is controlled by R to the D, and we're going to formalize that by stating it as a lemma. That double star in lemma 9 is controlled by the thing that we want. Okay? All right, so this, I'm going to defer the proof. In fact, I'm going to put this off to the end and hope that I get to it. I think I can probably get at least to a sketch of it. All right. All right, so now let's return to the proof. Just take this for granted for now. We're going to return to the proof of the main thing that we wanted, all right? Or the main thing that we had reduced matters to, which is that the localized half-order derivative dnr applied to A was controlled in L1 on F intersect QR by the measure of QR. All right? So this is what remains to be done. Okay? So let's recall that H of ys is the regularized version, or maybe let me say it this way. It's comparable to the distance from ys to f, and H is an R-lib, right? It's a regularized parabolic Lipschitz function. Okay? So now I'm going to define a variant of A. I'm going to call it AH of xt. It's going to be defined to be A of H of xt, comma x, comma t. Okay? So in other words, right, remember we had these level set graphs A of r xt, and we're letting r vary along this contour. Okay? All right. So the next step is to replace A, and really this A, remember, is A0. It's the original boundary function, okay? The function whose graph defines the boundary. To replace A by AH. So notice, of course, that they agree a lot of the time, right? Because when H is 0, that is when xt is in the set F, then this is 0. And remember, A of 0 xt is the original A, all right? Okay. All right. So let's recall that the kernel of the localized half derivative is something that I'll call, I hadn't defined this notation before, I'm going to call it k tilde r. Remember, there was also a kr. Let's not confuse them. This one is the t derivative of v times phi r, where phi r, remember, was a smooth bump function, a smooth cutoff that localized v. V was the kernel of the parabolic fractional integral h minus a half. Okay? We also had, okay, so don't confuse with KR, which was the far away part. All right. That was the kernel for the air term. All right. The far away part. All right. So K tilde is going to be the kernel of the local part. And it satisfies at a point xt. This is going to be bounded by the length of xt to the 1 minus d. Of course, that's just the homogeneity of the parabolic fractional integral. Sorry, I lied to you because I'm applying a time derivative to it. So 1 minus d is the homogeneity of this guy, and then when you apply, in effect, 2 orders of differentiation, right? Because the t derivative comes twice, you get minus 1 minus d. All right, and that's times then. Remember, this is a smooth cutoff. This keeps us inside the ball, the parabolic ball, where the length of xt is less than 5r. Okay? So let me remind you of Lemma 7. Which said that if you look at the difference between A of H of ys, ys, and A of ys, that difference is on the order of H of ys, which of course is comparable to the distance from ys to f. Okay? So then we have, for xt in QR, which is where we're working, where we're trying to get an L1 estimate, if we look at the difference between dnr of A and dnr of AH, of course, what is this? This is the integral of this truncated kernel K tilde R. It's a convolution times A of ys minus A of H of ys, ys, dy ds. Okay? And now I'm going to bring absolute values all the way inside and use these various observations. Okay? So this is going to be less than or equal to up to some constant. I'll say that in a second. Okay, so we have this size estimate. For K tilde R. We have that this difference here is like H of ys, which is like the distance to F. And everything is taking place inside of, let's say, 10QR. Because, remember, xt is in QR, and because the support condition for this guy, x minus y, t minus s has parabolic length less than or equal to 5r. Okay, and of course, notice for free, I get to put f complement here. All right, because this vanishes on f. All right. Okay, and I'm going to give this a name. I'll call it, let's say, JF complement of the indicator of 10QR, evaluated at x and t. And notice what this is. This is just a parabolic Martian-Kivitz integral. Okay? Whose properties we understand very well. This is classical, right? So when you take the L1 norm on the complement or on F of this guy, of JF complement of the indicator of 10QR, it's just the standard facts about Martian-Kivitz integrals. You're just going to pick up the L1 norm of this thing, which is like the measure of QR, which is what we wanted. This is just an exercise in using Fubini's theorem. Okay? All right. And so this is a good time to stop. Let me just conclude with a punchline here. Hence, enough to prove star, that star, with AH in place of A, because the error is control. All right, so that's a good place to stop. Any questions before we shut down for a coffee break?